apply this to word problems involving this related rate. So in this case, well, we started with a very classical problem in which we have a sphere, a spherical shape in which the volume is getting larger or smaller. In this case, we got the situation in which it's a snowball assumed to be of a spherical shape. Due to the melting, the radius of that sphere got smaller, and as a consequence, the volume got smaller as well. But in this case, that happened over time. That's why these two variables, both the volume and the radius, are functions of a new variable that is controlling everything in the background, in this case t, or time. All right, so well, we did one example. We identified the given information, we identified the equation. Well, since in this case it was not clear what it was, in some cases you may be given the equation, in some cases you need to figure out what we're talking about. Well, in this case, well, it's kind of clear that it's a spherical snowball, and in this case, it's relating volume versus radius. So what would be the equation that relates volume and radius? Well, the volume of a sphere in this case, because of the spherical shape. We did a calculus, and then we plugged in the numbers, and in this case, we got the final result. All right. So what's all these important points are summarized here in the next page. Well, so a very common mistake is to plug in values early in our process. So, well, in some cases it's okay to plug in those values early. That's only when those variables are not changing at all, because we're going to look at other situations in which not just two variables are into play, but actually three variables, and the three variables might be changing over time. And well, in some cases one of those variables may not be changing. For those, we can plug in the value of r. So in this case, notice how we didn't plug in r right away to get the volume, because if we plug in r equals to 20, that's going to be 20 cubed times 4 pi over 3. That's going to be a number. Take the derivative of a number. Well, that's 0. Well, that's wrong, because we're trying to find how fast is the volume changing, and well, clearly the volume of the sphere is changing at whatever rate, and that would be inconsistent with the result if we differentiate a number. Well, what other situations can we use? For example, we can have a similar situation of the area of a square changing over time due to the length of the side being changing. Triangles, circles, rectangles in general, volumes or surface areas of cylinders, the sphere, the surface area of the sphere, the volume of a box. Well, we will have a bunch of information to get this, putting them together. The Pythagorean Theorem, that's another very important one that we're going to use actually. The trigonometric functions and their ratios, SOHCAHTOA ratios, to get, well, not in this case, well, it could be the angles, it could be only the ratios. And ratios of similar triangles, you know, when we have the same triangle with the same angle, it's just a bigger triangle. All we do is equate the sides of the triangles to their corresponding, to get the corresponding ratios and proportions. All right, let's look at one more example. So what do we have? A 20 feet ladder. It's leaning against a wall and begins to slide. So the question is, how fast is the top of the ladder sliding down the wall when the bottom is 12 feet from the wall and sliding away at a rate of 5 feet per second? All right. Number one, let's draw a picture. So we have this wall right here. And we have the ground right here. All right. So what do we have? We have a ladder. And this ladder is, number one, is 12 feet long. All right?
No, it's 20.
What is it? Oh yes, it's 20. Yeah, the 12 it's the feet. Thank you. So 20 feet long. All right. So this is the situation. In this case, the ladder is going to slide down vertically, and consequently, so the fact that this height reduces, that's going to make this horizontal distance to increase. All right. So that's the situation here. So that ladder goes down and it goes forward. All right. So what else do we have? So the fact that we have this okay, let's look at each component individually. Number one, we have a height y that we don't know. For now, we don't know it. We don't know what that is. Also, this part of the ladder is sliding down at a rate that we are going to call it dy dt. So that height at which the ladder is leaning at, it's going to go down at a certain rate. That's actually the question. How fast is the top of the ladder sliding down? So that's going to be our unknown. What do we know for the horizontal direction? Well, in this case, x equals to, well, 12. That's 12 feet away from the wall. And they're telling us dx dt is, so it's sliding away at a rate of 5 feet per second. Now, so that's the length L for the ladder. However, what's dl dt? Any ideas on what would dl dt would be? It's zero. How come it's zero, by the way?
The length of the ladder.
Exactly. I mean, the length of the ladder remains the same. I mean, they're telling us it's a fixed length. You know, it's 20 feet long, unless they told us, well, at the same time that ladder slides down and horizontally, I don't know, maybe the ladder stretches or compresses, but that's not the case. But in that situation, we would have a rate for the length of the ladder. Well, in this case is 0. Okay, so here is a picture with all the pieces of information together. Let's make a simpler picture. And that simpler picture would be, notice the shape that we have here. It's just a triangle, a right triangle in particular, right? So there is number one, there is one model that relates the three sides of a right triangle. What is that model? The Pythagorean Theorem. So in this case, with the labels L, X, and Y, so adapted to those labels, so we should go about L squared plus equals to x squared plus y squared. All right. So in this case, let's do the calculus on the Pythagorean theorem. So we will notice in this case all variables change with respect to time. All right. So that's really what we're seeing in the background. And I write this next to the function that we're going to differentiate, just so you can see the dependence of these variables L, Y, and X. Well, so the derivative of 2L of L squared, that's 2L, but in this case dl dt. The derivative of x squared is 2x dx dt. And the derivative of y squared equals 2y dy dt. Okay. However, we may go about canceling some of the terms, because, well, what's dl dt equal to? Isn't it 0 because the length of the ladder is not changing at all? Well, so we can already 0 one of the terms out. Well, that means we're going to be left with 0 equals to 2x dx dt. plus 2y dy dt. All right, let's put a check mark on the information that we have. Okay, do we know x? Yes, we have it here. Do we know dx dt? Yes. It's also here. What about the y dt? Well, that's actually the question, right? What about y? Do we know y? We don't know y. However, we have enough information to find the value of y at this particular time when x equals 12, and of course the length of the ladder is 20. So let's set it up 20, x equals to 12, and let's call this y. So we're going to use the Pythagorean theorem to find that missing piece of information. And well, so that's L squared equals x squared plus y squared. So notice we're going to use this Pythagorean theorem twice. Once to find the missing quantity that we need to incorporate in our calculus part, and a second time to do the calculus to get the rate of change that we are being asked for. So L squared, that's 20 squared, equals x squared, which is 12 squared, plus y squared, which is y squared. We don't know what that is. That's going to be 16. So that's going to be 400 equals 144 plus y squared. That's y squared equals to 256.
And square root is 16.
Y equals to 16. So this is equal to 16. And that's the number that we now know what it is. So we're ready to plug in the known information into the derivative to find that missing rate of change. By the way, from last time, what's the name of this equation? We gave it a special name last time, remember? So, isn't it the related rates equation? Because this equation is relating the rates that we are finding. So, well, that's going to be number 1. 0 equals to 2 times x, which is 12, times dx dt, which is 5. I'm going to put the units in the end. Plus 2y, which is 16. dy dt is simply dy dt. So 0 equals to 12 times 5, that's 60 times 2, that's 120. Plus 32 dy dt. Well, so let's solve this baby equation. It's a linear equation for dy dt. So dy dt, or rather 32 dy dt, equals negative 120. So dy dt should be negative 120 over 32, which reduces to negative 15/4. And in this case, we may go about write down the units. It's important to write the units at least at the very end of the problem. So that's feet per second. All right? Feet per second. Well, to make sense out of the result, notice the sign of the result that we obtained here. It's a negative number. How does that make sense with the situation that we're working on? Well, because this distance y is getting smaller all the time because it's sliding down. If otherwise we were given that rate of change at which it's going down, well, we would have been asked for dx dt, and since that's sliding away, that's going to make a larger, or that's an increasing distance away from the wall, and in that situation we would have obtained a positive result. And in fact, we were given a positive result to begin with and to make sense out of it. All right, so that's another example in related rates. So let's see, what else do we have? Profit function. This is a very short problem applying to economics, if you will, to business analysis. So a boat chart total profit from selling X number of outboard motors is given by P equals negative X squared plus 1000X minus 2000. If the outboards are selling at a rate of 20 per week, how fast is the profit changing when 400 motors are being sold? Alright, so this one, let's identify the information. So in this case, rates. So they're giving us dx dt, the number of outboards sold per week, right? That is 20 per week. And also the other rate will be the change in the profit with respect to time. And in this case, well, that's the one that we don't know. Alright? So we need to calculate that one. Alright. So we have a function. Actually, we're given a function. That's what makes this problem very straightforward. Just do the calculus on the function. So we have the function. Let me write it down again. So that's p equals to negative x squared plus 1000 x minus 2000. So dp, in this case, dt, and that's because, again, what's going on in the background. So really, this function, this profit function, it's a function of time. Negative x squared, a function that changes over time, plus 1000 x that changes over time, and then minus 2000. So I did write that variable t only for the first example, the one that we did last time, just to get it, so we don't forget that these functions are changing with respect to time. This time I'm just going to write the function, but I'm not going to do the calculus with the t. Of course, if you know for sure that this is a related rates problem, you don't need to write the t. So I'm writing them just as a reminder that these are functions that vary over time. So that's going to be the derivative, it's a negative 2x plus 1000. But in this case, this x varies with respect to time. Alright? And I think we can plug in all the information. So they're asking us how fast is the profit changing when 400 motors have been sold. That's x equals to 400, and we also know the rate at which they're selling at a rate of 20 per week, which is this dx dt. Okay, so dp dt will be then negative 2 times 400 plus 1000 times the x dt, which is 20, and well, so that's going to be negative 800 plus 1000 times 20, and that equals to 200 times 20, which is 4,000. And what would be the units for this result? So if P is profit, how do we measure profit? Which units do we do? Dollars, alright, $4,000, and in this case, per week, right? So what would be the conclusion? Are you making money or are you losing money?
Positive profit.
So it's positive profit. That should mean that you're making money. So what if for some reason you get a negative number? So it means that you're losing money. Then you will have to look into your company, what's going on. Maybe you're making your products too cheap, or maybe something's going on in the production, making this negative profits, you know. And let's look at one more example. So what do we have? So a woman is watching an unidentified flying object from the ground through a telescope. The unidentified flying object is flying at a constant altitude. So constant altitude, there's something that it's not changing. We can start highlighting this. That's going to be important when setting up the picture. And at a speed of 10 miles per minute towards the point directly above her. At what rate is the angle of her telescope changing at the instant the UFO is flying 24 miles away from her? So that is as measured horizontally along the ground. Alright, let's draw a picture for this one. So number one, we have someone, and there's a telescope here. Alright, there's a telescope, and we have the ship. Forming, essentially it's forming a right triangle. Alright? So that's the picture. Now what's going on? In this case, the object is flying into the direction in which she is looking at the ship. Alright, the alien ship here. So this is going to cause, if the ship is coming directly towards her, so she will have to raise the telescope so she can see, so she can keep still seeing the ship clearly in the middle of the scope. That's going to cause a couple of things. Number one, that the angle changes, right? Changes. Now, what would be the sign? Let's start looking at let's start analyzing the values and the variables here. So what would be the sign of the change in the angle? Positive or negative? So changes positively, right? And well, since the ship is getting straight to the woman who's watching it, well, what is this? How is this distance changing? Is it changing positively or is it changing negatively? Negatively, exactly, right? It's getting smaller, so that's going to be changes negatively. Now, what about the height? Does the height change? No, they're telling us that it's flying at a constant altitude of 7 miles. So height remains.
We don't know the height.
Yeah, 7 miles. Mm-hmm.
So how is the UFO 7 miles above?
Well, it's 7 miles from the ground, above the ground. Mm-hmm. Height remains constant at 7 miles. All right, so they're not telling us that the ship is going upwards or downwards. No, it's remaining constant and it's traveling, or it's flying in a horizontal direction. So that means the height has to be constant. So that's the picture. That's what we have. So the thing here is, at what rate is the angle of her telescope changing at the instant the ship is 24 miles away? Alright, well, 24 miles away, that represents horizontal distance. Are you guys with me with that? Okay, and well, okay, I'm going to draw another triangle, and that triangle that I'm going to draw is to set up a function, to set up so we can do the calculation. This one is just a picture of the situation. So number one, let me draw another triangle. So in this case, the variables in question are theta, x, and y. Well, in this case, we don't care about this diagonal distance. We can call it L, but it's actually not in the conversation here, so we can just disregard that part. All right. So, well, We know y remains constant at which is 7. However, x doesn't remain constant, right? X is something that we will figure out, and in this case, it is x what changes with respect time. It changes over time. So the closer to the later it gets, it's going to vary at a whatever rate. All right. So the rate, the instantaneous rate at which this distance is changing precisely at the moment where x equals to 24. What's that rate? Are they giving us this rate?
No.
10 miles per hour towards the point directly, right? So it's changing at that point. So that's 10 miles per hour. All right. Oh, per minute, right? Okay. So in this case, since the angle is into the conversation, here is where we will need to use our trigonometric function. So number one, which trigonometric function relates the opposite to the angle and the adjacent to the angle? It's the tangent function, right? So let's write down a tangent function. So tangent theta equals y over x. Okay, in plain variables for now. Now the question is, again, well, we already did this a few times. Let's do it again before plugging in numbers or doing any calculus. Is the angle changing?
Yes.
Is y changing?
No.
No, so we can go ahead and plug in for whatever doesn't change. That's going to be 7. Is x changing?
Yes.
It does, right? All right, so I'm gonna, before we can differentiate this function, we will write this in a way that we can differentiate, because we cannot differentiate x while it's in the denominator. So let's write it down, or write it up to the numerator, 7x to the negative 1. And well, let's differentiate both sides of this equation. So the derivative of tangent, what's the derivative of tangent again? Secant squared theta, just secant squared theta. I'm missing something, right?
Oh, yes. D theta.
D theta dt, right? Because the angle is changing with respect time, right? So d theta dt, and that equals to negative 7 x to the negative 2. But again, this distance also varies with time, dx dt. Okay? So I think we have an equation ready for us to do these calculations, because, well, let's analyze this derivative and see what we have. Okay, do we know x? It's 24. All right? Do we know dx dt?
Yes.
10 miles per minute. All right? Now, when it comes to secant squared, well, there's a couple of ways to go about this problem. So number one, you might want to take the square root. Okay, rather, no, not take the square root. No, because we need to solve for d theta dt. So this is usually a tricky one, because what do we do with the trigonometric function? So ultimately, we are not going to care at all at the trigonometric function. So let's solve for d theta dt first. And then we're going to run into a situation in which we will be apparently missing some information. But don't worry, we will get that piece of information that looks missing. So d theta dt equals to 1 over secant squared theta times negative 7 over x squared dx dt. And again, let me keep writing down check marks for what we know, that dx dt and the x. All right, we don't know what secant squared is. However, that seems to me like one of the hard trigonometric function to work with. How about we rewrite this secant squared that it's in the denominator to the numerator, using a reciprocal function. What would be the reciprocal of secant squared? What's that?
Cosine.
Cosine squared, right? Cosine theta, and I'm going to write it this way, quantity squared, for a reason. You'll see why. Negative 7 x over x squared dx dt. Now, we can already plug in for x and dx dt, no problem. However, we need to find cosine, but that cosine we're going to get it from the triangle that we set up at the moment where x equals 24. But well, cosine, using SOHCAHTOA, what's the definition of cosine?
Adjacent upon hypotenuse.
Okay, so we know the adjacent side, right? Do we know the hypotenuse? No, so we need to take a little side trip, calculate that missing piece of information before we can plug that in the final equation. Well, so we're going to use the Pythagorean theorem. That's L squared equals x squared plus y squared, where L squared, we don't know what that is. X squared equals 24 squared plus 7 squared. 625.
And then it's 25 is L squared.
And L equals the square root of 625, which is in this case is 25. Well, technically this should be a plus minus because of the square root property, but come on, we're working with physical distances, so that plus or minus doesn't make sense at all. So we're just taking the positive part. Now we can answer the question, what's cosine using the triangle? So that's d theta dt equals 24 over 25 quantity squared times negative 7 over x squared, and dx dt, which is 10. And using a calculator to simplify this madness should give us the following result. d theta dt equals 0.117. What will be the units in this case? That's the big question. Units for angle. How about radians per minute?
I got something else on the calculator.
You got something else? Oh, actually it should be, no, that's fine. It should be, it's actually negative right here, right? It's negative because that distance, that horizontal distance gets smaller. So technically, I should have added a negative value here, all right, when it came to the picture, because in the end, negative times a negative becomes positive, and that should make sense with the end result because, well, what's going on with the angle? The angle is getting bigger every time, so that related rate has to be a positive value, right? So yeah, that's what I got. 0.1117. If you got something different, it might be because of the syntax when typing the values for the graphing calculator. All right. So that's what I had for today.